In this lecture, we will start our discussion on computing aerodynamic flows, and we will try to connect with the theory that we have learnt over several weeks now. You may recall several lectures before we have discussed about a typical passenger aircraft with a figure like this, the different features, the different shapes, sizes, etc., with a rough sketch. And we discussed that in order to understand its aerodynamics or aerodynamics of other vehicles, even natural flyers, etc., we have to understand a lot of basic concepts. So, that was the theory part of the course. So, let us recall briefly about the different things we have touched upon. So, we have looked at different kinds of shapes and surfaces, and from a figure like this also it is very clear that a typical passenger aircraft, it has so many different shapes, surfaces involved in the entire geometry, and they have to be deflected, they have to be controlled, etc., to make the aircraft fly appropriately along its trajectory and complete its mission. You have to run the engines to generate thrust. You have to make the aircraft take off from an airport, reach cruise conditions, then again glide and come and touch down safely on the airport, and so on. So, shapes and surfaces on the aircraft make this happen along with the engine which generates the desired thrust. At a more fundamental level, we have a flow, an air flow, and when that occurs past the body, we know that there is a pressure distribution which develops on the body along with the skin friction or the shear stress that develops, and we learnt in due course that such dimensional parameters could be even non-dimensionalized and expressed in terms of pressure coefficient, skin friction coefficient, etc. And if you sum up their effects on the surface geometry, then you can compute the force, moments, and typically on a body like this you would have 3 forces, 3 moments which will be coming out from such an integration of pressure distribution and skin friction. If you look more deeper into the flow, for example, you can look at it from an Eulerian perspective or a Lagrangian perspective, and then if you are looking at a particular control volume somewhere in the flow field, then you are essentially looking at how the properties within that control volume are changing over time, while if you are following a particular fluid element over the aircraft, then you are following a Lagrangian approach. So, we came about the concepts of streamlines, streak lines, path lines, and then we said that if we can simplify the flow problem to a steady one, then all of them essentially mean the same. So, steady flow is a very important approximation that we often make in discussing aerodynamic flows over bodies of interest. And then we looked at the different conservation equations. From an integral perspective and a differential perspective, we looked at conservation equations, and we looked at mass conservation, momentum conservation, energy conservation, and when we compute flow fields, that means when we are looking deeper into calculations of pressure, velocity around a complex geometry like this, we certainly have to solve these governing partial differential equations in some manner. So, that is what we call as computational aerodynamics or computational fluid dynamics, often abbreviated as CFD. And over the next few lectures, we will try to understand how that approach of looking at the flow field is of enormous relevance, and that also would complement the theory that we have learned, the theoretical background that we have achieved over the last few weeks, how it can enrich it further. And then after we are done with the computational part of the course, we will look at even the experimental approach. So, then we would have looked at all three major approaches of looking at aerodynamic studies. So, going back to the conservation equations, we also in between covered a little bit of fluid kinematics, you would remember. So, we looked at a fluid element and we tried to understand that under the given stresses which act on the fluid element, how does this fluid element respond. So, it responds with a time rate of change of the shape, which we often designate as a strain rate. And we find that the fluid element may be rotating for certain kinds of flows. So, that is how we came across rotational flows. So, this is a good time to recall all that we learned in the theory, because some of it or most of it would actually come in even when you are trying to compute the flow, and then the theoretical background that you have acquired over time would be very, very useful and absolutely essential to understand even the significance of the computations. So, when you look at the computational results, you will be able to figure out that what kind of modeling you might have done in order to solve for the flow field, what kind of conservation equations you might have used to solve for the flow field. So, this is the kind of insight we would also like to achieve in this part of the course. Moving on further, we tried to look at inviscid and viscous behavior of the flow. That was a very, very important part, where we tried to distinguish between the effects, and in that context we looked at potential flow and boundary layer theory very briefly. We then looked at compressible and incompressible flow. Further, we looked at the basic nature of laminar and turbulent flow. So, these are very, very important aspects of the flow field. So, we will try to revisit these aspects once again when we look at the numerical solutions of flow fields. Then we did a bit of airfoil geometry. So, if we take a section of the wing, we will see an airfoil section here. So, we learnt about airfoil geometry, and then we looked at how the Cp versus x by c looks at different angles of attack, how that may be changing as the angle of attack changes. And then again, if we integrate the Cp and Cf, you can generate Cl alpha, Cd alpha, Cm alpha curves. We looked at them. We looked at flow separation and stall, and we also looked at how that may be alleviated by using high lift devices. which are deployed during takeoff and landing, and then essentially we use so called multi element airfoil sections. And then from the airfoil section we went into the finite wing, and therefore, you would have a wing plan form, it might have sweep, it might have taper, it may have geometric or aerodynamic camber, and then we also try to compare the characteristics between a finite wing and an infinite wing or airfoil. We also looked at delta wing and how it would behave at comparatively higher angles of attack. And during the last few lectures, we looked at compressible flow in more detail, where we looked at shock and expansion theory, flow through CD nozzle, and then flow past an airfoil at different free stream Mach numbers over a wide range, starting from compressible subsonic to hypersonic or at least high supersonic conditions. We looked briefly about the concept of shock wave boundary layer interaction, a little bit on shock tubes and hypersonic flows. So, we have done a brief study of many aspects which builds up the theory, the theoretical ingredients that we need to understand the area broadly, the aerodynamics area broadly, and now we are rightly pitched to also look at a little bit of how the computational results look like when you try to compute aerodynamic flows past different geometries. So, to keep things simple, we will begin with a comparatively simple geometry, and we will try to look at how flow solution looks past it, that is the airfoil section. So, we will pick an airfoil section and we will try to look at the flow field around it, and then we will try to see how the theories that we have learned during the last few weeks, how they fit in there. Can we understand the result of the flow computation with our theoretical background? That is very important for us to assess. So, with that in mind, we move on, and we have a picture basically of a flow field which has been computed using some governing equations. So, at this point we are not very sure what governing equations have been used to solve it, but from our theoretical background, let us try to put arguments through and let us try to figure out that most probably what kind of governing equations might have been used for this solution. So, starting from the appearance that we have here, we have a set of colors or contours which are shown in this figure. You can see deep blue color some distance away from an airfoil section. So, this is your airfoil section, and then as you come closer to the airfoil, you find that the colors are changing. And then starting from the leading edge part of the airfoil, and then the surrounding regions around the airfoil, and then also the wake region of the airfoil, there are color changes. So, the color change must be demonstrating some property changes in the flow field. So, most likely it seems to be representing in some way the velocity distribution around the airfoil. So, it could be that the colors are changing based on the velocity magnitude. So, you might imagine that the velocity vector at every point in the flow field, since this is a two dimensional one, will have a u and v component. So, what if you square and sum them up and then what you have is essentially the magnitude of the velocity. So, the colors may be representative of the magnitude of the velocity, because then you do not need to make a separate plot for the u distribution and the v distribution. That would be the advantage. Okay. So, this is the way we try to put our arguments through and try to figure out that what may be a possibility, a rational possibility. Having done that, we will then have to go deeper and try to search for more answers as we raise the questions and try to answer them. Okay. So, we have learnt about airfoil geometry, for example, and then let us try to revisit what we tried learning there. So, there we said that in the xy system, we can place the leading edge of the airfoil at 0 0, and then we take a certain length along the x axis, and that would essentially give us the chord length of the airfoil. So, we often designate it by c, lowercase c, and the straight line that that is of c length from the 0 0 point is essentially the chord line. And then if you have a cambered airfoil, then you try to define a camber line which will be different from the chord line, and then you distribute a particular thickness distribution equally above and below the camber line to generate the shape of the airfoil, and it ends with the trailing edge at the C 0 point. So, the coordinates of the trailing edge essentially is C 0. So, this would be a typical shape of a cambered airfoil, but here the shape that we are looking at over here in the plot of the flow field, which is a computed flow field, seems to be symmetrically disposed about the chord line. So, in all probability this is a symmetric airfoil, and it does not seem to be a very thin one, because if you consider this to be the chord length, then the maximum thickness of the airfoil seems to be of the order of about 12–15%, though we are not actually measuring it and trying to find out, but still this could be a reasonable guess. So, it is a symmetric airfoil. Moreover, the flow field also seems to be symmetric around it, and therefore, in all probability this is occurring at an alpha of 0 degrees. And for a symmetric airfoil, the zero lift angle of attack happens to be 0 degrees. That means, there is no net lift force that this airfoil is generating in the given condition, and therefore, you can assume that the pressure distribution, the skin friction distribution, etc., will be symmetric or practically identical on the upper and lower surfaces. Now, why are we talking about skin friction at all? Well, there is something that we can probably smell here, that there seems to be a velocity difference between the far field and the region around the airfoil, and therefore, they seem to be due to viscous effect. So, there is certainly a boundary layer formation which is changing the colors around the airfoil. Moreover, it seems to be thinner closer to the leading edge of the airfoil, and it thickens as it moves downstream, and the red portion probably has the highest velocity deficit, that is also extending into the wake region of the airfoil. So, these are things that we can cleverly guess from what we can see from the picture. Therefore, most probably viscous flow equations have been solved over here. So, we have learnt about Navier-Stokes equations which can generate viscous solution. We have also learned about boundary layer equations, but then we learned that the boundary layer equations apply very well if the boundary layer thickness is very small compared to the characteristic dimension of the flow. So, in this case the characteristic dimension of the flow happens to be the chord length. Now, there are regions towards the later part, that means closer to the trailing edge part of the airfoil, where the viscous dominated region seems to have become much thicker, and therefore, just solving the boundary layer equations may not be good enough. Moreover, boundary layer equations may not give you the complete flow field information, it will just give you the information within the boundary layer. While here what we are observing is, we have information about the complete flow field around the airfoil. That means, in all probability we are solving the Navier-Stokes equations, which is not only confined to the viscous regions around the airfoil, but looking at a bigger domain within which the airfoil is placed. And also we can make out that the flow is numerically set in such manner that a uniform flow is approaching the airfoil from upstream direction, and it is impinging on the airfoil. Close to the leading edge of the airfoil, the velocities are becoming very small, and you can imagine that close to the leading edge you have the stagnation region. There is a specific point which is the stagnation point, where you can expect the flow to come to a halt. Additionally, from the features of the flow field, you can figure out that it seems to be a low speed flow. It seems to be a low speed flow, because you are not seeing any features which you have learnt about which characterize high speed flows, like shock waves, expansion waves and things like that. So, you are not seeing any trace of such features in this flow field. Therefore, it appears to be a low speed flow. So, we could infer quite a few things already, because we are watching the flow with a lot of care. So, this kind of intuition needs to be developed over time. So, as student of aerodynamics, we need to inculcate this habit of trying to probe deeper into a solution and trying to figure out that what is working behind it. So, we are looking at a streamlined body, and we have looked at wakes behind both streamlined as well as bluff or blunt shapes. And here, of course, because it is a streamlined body, the separated region behind such a body is obviously going to be thin. That means, the wake is apparently a thin wake. Now, what you might find out is that if you were to work out the velocity distribution in the wake region, it may vary like this. And there is a momentum deficit that is caused in the wake, which equates with the drag that acts on the body. So, from this flow field information, you cannot measure drag or lift on the body, but you can imagine that you can still make use of this data to obtain the drag in two possible ways. That means, here if it is velocity data, if you take the momentum content in the wake region, and then you try to compare it with what is coming in from the free stream uniform flow, then there will be a difference between the momentum contents, and that incidentally will be the drag acting on the airfoil. Another way of looking at drag is to integrate the pressure and the shear stress distribution, and thereby find out the axial force component. And here, since alpha is 0, axial force component will give you the drag. So, both ways you should be able to compute it, but if you are just given this plot and no other data, then possibly you cannot guess what pressure and skin friction distribution is like. So, the best bet would be to make use of the velocity distribution and trying to compute drag. So, we will discuss more about this idea later in the course when we discuss about experiments in aerodynamics, where through a wake survey technique you can compute drag on an airfoil. So, coming back to this, that we are looking at a thin separated region, then we know that the pressure drag will be of a very low order, because not large sections of the body is susceptible to drag. Maybe the flow has separated somewhere closer to the trailing edge, and you have a narrow wake which is formed, and therefore, bulk of the drag is coming from the skin friction. Again, we do not know precisely what kind of Reynolds numbers are involved here in this flow. So, if the Reynolds number is comparatively large, then this flow could also be a turbulent flow. And then we know from some brief calculations that we did on a flat plate that skin friction coefficient would be larger in the case of turbulent flow compared to laminar flow. And again, there is a separation which is caused towards the trailing edge part of the airfoil, where the pressure gradient becomes adverse, and that is the biggest reason behind flow separation being caused. Also, we know that over a range of Reynolds numbers, if you try to look at the flow field, there would be variations, and then for a comparatively lower Reynolds number range for airfoils, typically if you are looking at the flow fields at 10 raised to the power of 4 or 5 order or even lower, then you are looking at low Reynolds number range. For passenger aircrafts and things like that, we typically talk about Reynolds numbers range of the order of 10 raised to the power of 6, 7 or could be even more. So, we talk in millions. And then we learned about these CL alpha plots, and we learned that for symmetric and cambered airfoils, how the zero lift angle of attack changes. So, for a cambered airfoil, you had a negative zero lift angle of attack, and therefore, the whole lift curve shifts towards the left. But here in our diagram, it seems to be a symmetric airfoil. So, therefore, in all probability, the CL alpha curve would look like this. If you were to see the pressure distribution on the airfoil section, if that data was made available, then you would see that the upper surface and lower surface pressure distributions would become identical, because the flow seems to be absolutely symmetric about the horizontal axis or about the chord line. So, only when the symmetry breaks about the horizontal line, there is a difference in pressure between the upper and lower surfaces, and then there would be a normal force generation. In this case, the upper surface and lower surface pressures are expected to be the same, and therefore, there would be a single line. But when it changes its angle of attack, when it becomes other than 0, then you would find that there would be an area enclosed within the two curves, and the curves would separate out. And as you take it to larger angles of attack, the area increases. So, those features would become apparent at larger angles of attack. Of course, for a cambered airfoil, even at alpha equal to 0 degree, there you would find that the upper and lower surface pressures are not the same. Therefore, it generates some lift at alpha equal to 0 degree. Here are a few more points we are trying to make. We know that the region which is affected by viscosity would be a rotational flow region. So, that is where if you follow a particular fluid element, you would see a rotational flow that is occurring within it. And therefore, the region which is in non-blue, typically if you are talking about colors, those are the regions where the rotational effects will be stronger, and that too the reddish region seems to be the most rotationally affected region. One may say that if you are into the blue region, perhaps you can think about the flow to be an inviscid kind, which is not a very bad approximation really. But next to the airfoil and in its wake region, for example, you have a situation more like this in the lower figure. As I was saying that there is a deficit in momentum in the wake region, and that helps us to evaluate the drag force. But if you were to look at a completely inviscid model including the flow around the airfoil, then there would only be a normal stress acting on the airfoil through the pressure. There would be no shear stress, which is a tangential stress, and therefore, slip of the flow over the airfoil will also occur, because there is nothing that holds back the flow on the surface of the airfoil. So, if it was a purely inviscid flow, not only beyond the viscous region, but also next to the body, then this is how the flow would look like. So, you may imagine that the velocity magnitudes could still change, but then there would be local acceleration and deceleration, but there would never be a zero velocity condition occurring on the surface of the airfoil. While for a viscous flow, you would have a no slip condition on the surface. Further, we remember that in the viscous regions, the viscous shear stress becomes active, and when we are looking at a two-dimensional flow field, we only have the tau x y or tau y x components, which comprise of the viscosity coefficient multiplied with these two velocity gradients, del v del x and del u del y. And within the boundary layer region, you will find that this is the main driving force, the del u del y. You also remember about the basic concepts of streamlines. That means, if you were to plot the streamlines, you would be able to see them here. There would be a stagnation streamline, while the others moves past the airfoil like this. So, there are so many theoretical concepts which are of use, which we are trying to fit in order to interpret more and more about the flow field. So, we will discuss on these aspects further in the upcoming lectures, and therefore, our approach of looking at computational aerodynamics or fluid dynamics would be to see how far our theoretical knowledge can be rationally applied in order to understand computations better. Thank you.